Record on this computer. Yes. Thank you. As always. Armando, where is that? It's pretty.
Iceland.
Okay. Iceland?
Yeah.
Cool.
There for a study abroad program.
Cool. There are humans in Iceland. I'm a dumb American. I hate to say that. Okay, so 308. not a single response.
I guess we can do 308 now.
Okay, we'll do some 308. Okay, so not sure if this is all visible, but in the last couple of classes, we've seen where R comes from and where C comes from on a node. So if you have two stages, let's see if my pen was working earlier. If you have two, yay. If you have two stages, in between the stage, there's a pole. And this node has some capacitance. It's the sum of the capacitance contributed by the wires and the transistors. But in our case, we're ignoring the wires. So it's the sum of the capacitance from the transistors. So going over here, you might hit a gate or a base. Going back this way, you might hit a collector or emitter. But all of those contribute capacitance to this node. And then when, let's say, you want to raise the voltage at this node, so you give this, maybe this is an amplifier, and you give this a voltage to make this node go up. This node has to charge. So for those in 307, when you're changing the voltage at a node,
charging, discharging,
charging or discharging a capacitance. So this right here, this is trying to set the voltage on that node. That means it's charging this capacitance or it's discharging this capacitance to change the voltage there. And so the paths that put current on this node, those are, they're not infinite current, so they are acting like resistors. So you have the capacitance contributed by the transistors, and then because you don't have infinite current, that's behaving like a resistor, and you end up with something that looks like this. The voltage you're going to, voltage going to node being changed. And this right here, through that, this is a low pass filter, and low pass filters have one pole over J omega RC. This R and the C are exactly the R and C that you found for that node. And then if you want to know the omega at that pole, it's whatever omega times whatever its multiplier is. In this case, it's RC. You want to make that 1. You want to make it the same magnitude as this term. So to make the magnitude of this term equal to 1, your omega has to be 1 over RC, and that's where your pole is. That's where the denominator starts to dominate. Okay, and drawing that on a Bode plot, we talked about a pole. On the magnitude plot, it starts your gain to dropping, and magnitude again is 20 log of gain. I'll put absolute values around the gain, 20 log of gain, and as soon as you hit that 1 over RC, your 20 log of gain starts to drop at 20 dB per decade. Okay, and then for a pole, what happens to the phase?
It's a 90-degree phase shift over 2 decades.
It's a 90 degrees phase shift over 2 decades, and it starts a decade before and ends a decade after, and then you've got minus 90 degrees. Okay, is that up to there? Is that good? Okay. We've really been using the quick method to find the poles. We've drawn in, if we have you draw the transistor level circuit, and then you can draw in the capacitances, and then you see if the other side of the capacitance moves, and see if there's a multiplier, all that stuff. If that isn't clear, you can talk to me or watch the videos from previous classes. But what was my point? What's my point? Okay, so we've been able to find the pole basically using a quick method, just not having to do small signal analysis, just drawing in the capacitances on the transistor level circuit. But there's one value that you can't find without doing small signal analysis, and that's the zeros in this system. So let's do that math. Should I leave that visible? So let's do a BJT. I know I've been really BJT centric, but hopefully you can apply what we've looked at to MOSFETs as well.
MOSFETs are easy peasy once you know BJTs.
Okay. Got our 3 capacitances. Okay. So again, poles are easy. I shouldn't say that. You can use the quick method to find them. But zeros, again, you have to do small signal analysis. So you need a small signal model that includes the capacitances. So let me draw in the small signal model. So there's the small signal model. Now to make this useful to find poles and zeros, you need to add the capacitance in, and I'll add 1 in. Let's look at this first one. CBE is also C pi. You could call it CBE if you'd like. And it goes from the base to the emitter. So let's mark, this is the base, this is the emitter, this is the collector. So I know I've got a capacitance that goes from the base to the emitter. So I find the base and I find the emitter, and it goes right there. Okay, I'll give you 30 seconds to draw in the other 2 capacitances on the small signal model. I don't think that was 30 seconds, but let's give it a go. So the next one is C mu. C mu goes from the base to the collector. So you find the base, you find the collector, and it goes in between there. And we've got one more, we've got CCS. And it goes from the collector to the substrate, but oops, there's no substrate in the diagram. So just like for the MOSFET, how the MOSFET has the base kind of drawn separately connected to ground, we can do the source, the substrate here like this. And then, actually, let me move it over to make it a little bit prettier. And then we have the collector here, we have the substrate there. We know those have to be connected. CCS. Okay, where the capacitances are connected, is that okay? Okay, all right, so we have our new small signal model. And I think I've shown you this before, but the research group that I worked with, we were trying to build a radio that worked at 60 gigahertz. In other words, a wireless device that worked at 60 gigahertz. And you can imagine what, the model that we've been using, let me start the story over. The model we've been using so far without capacitances, for low frequency, that's perfect. That works well. But as soon as the frequency starts to go up, now you have to pay attention to the capacitance. Now, if you keep the frequency going higher and higher and higher, eventually you have to start taking inductance into account and all sorts of other resistances and other capacitances. And this is the model. I didn't have anything to do with it. I would love to take credit for it, but whoops, what did I do? I killed it. This is the model that we came up with. And we did all of our math using this model. So you've seen the small signal model with 2 resistors and 1 current source, dependent current source. This was the model we used, and it really worked well. It really predicted the behavior once we fabricated the chip. It really worked well. But just thank goodness that you don't have to use this model. We're just going up a little bit in frequency, so you can just take the capacitors into account and call this is good enough for the frequencies that we're at. Oops. So let's do this. Now, the reason why I'm introducing this is, again, the poles, they can be calculated just by looking at your circuit and not doing small signal analysis. It's just the 0 that you need to use this model for. So let's do the traditional circuit to use is common emitter. So let's remember what a common emitter is. Whoops. RC, V in, V out. Okay. Now, if tell me if this goes too fast. But I know the inputs on the base. I know the emitter's grounded. I know V out is on the collector. And then there's this RC. Where does the RC go?
Does it go to ground because we're doing small signal analysis?
Yes, so this becomes a ground. It goes from this node to ground, so it actually ends up in parallel here. And this is the middle frequency, in quotes. It used to be the high frequency model, but now it's the middle frequency model with the capacitances included. Okay, this looks really scary, but all of these capacitances, you get to treat them as resistors of size 1 over omega c or 1 over SC, whatever's more convenient. So let's find the gain. Let's find the gain. Let's see which one I need to do first. R out. Okay, R out. And we know R out equals V test over I test with the current going into and V out is just V test. They equal the same thing, but just for consistency, I'll do that. And then what's the 2-port rule for R out?
Ground V in.
Ground V in. So I'll put that on here. So V in gets grounded. And this is our picture now. And this looks like, this should scare you. Whoops. Try that. This probably looks very scary. But let's see if we can get rid of some stuff. Anything we can get rid of, we'll do purple.
R prime.
R pi goes away. You've got 0 on both sides. So R pi goes away.
And then the current source, GM.
So VBEs across R pi, it's 0. Get rid of the current source. So that looks good. The C pi, it's also going from ground to ground. So you can, if you have a capacitor with both sides grounded, you get to ignore that too. And then to make this a little bit easier to see, let's see if this fits down below. Okay. So let's get rid of some of that stuff. All this goes away. And this is grounded now. That's gone. Let's just do this. And what you have is, if you redraw this a little bit, what you have is it okay to scroll? Anybody still? Okay, that's good. Okay. What you have is, you have and here's where you get to treat your transistors, your capacitors as impedances. Okay. If you have two capacitors in parallel, what do you get to do to them?
Adam.
Add them. So I'm gonna do one more cleanup here. So I'll just cross this out and say, hey, I moved it over here. So now you basically have two impedances in parallel. So remember, this model is for when you have a high frequency signal coming in. So there's going to be some frequency. The signal isn't going to be DC for this model. You always want to use the simplest model you can. And if you have a DC input, what happens to all the capacitances?
They're opens.
They open and they give you your original small signal model back. So this is only for when you have a high frequency signal coming in. Now you have two impedances in parallel. Let's use over here. R out equals ZC in parallel with RC parallel RO. And then again, what's the impedance of a capacitor?
1 over J omega C.
Yeah, J omega C parallel RC parallel RO. Now, one thing when you do small signal analysis with this model, a good final step is to pull out the term. You know that at low frequencies, R out is RO in parallel with RC. It's a good step to try to pull that out. So let's treat this as a single resistance. So if you're doing them in parallel, you have J omega C times RC parallel RO all over 1 plus J omega C plus RC parallel RO. Just putting them in parallel. And then because we hate fractions, multiply top and bottom by J omega C. And what you get is RC parallel RO. That's 1 over 1 plus J omega RC parallel RO times your C. And in this case, your C is your CS plus C mu. All Okay, so is this a pole or a zero? Does R out have a pole or a zero?
It just has a pole.
It has a pole. So R out has a pole. So I said my whole goal of introducing this is to show you where a zero comes from. So this is not it. But now let me take this picture again. So we found R out. What we're working on gain. So if you have R out, what else do you need to find the gain?
GM.
GM. So give you a couple of minutes. See if you can do the small signal analysis to find big GM of the circuit. Sorry, I gave the annotated one. Let me clean this up a little bit. Oops. I just noted bib into zero.
Trying to keep it anonymous, you know.
Do you want more time or should I kick it off?
You can kick it off.
Okay, all right. All right, so what's the 2-port rule for GM?
V out equals 0.
V out equals 0. So let's draw that in. And now you're looking at this current. This is your I out now. Okay, anything we can get rid of?
The CCS
CCS goes away because you have 0 on both sides.
and the RO in parallel with RC.
RO parallel with RC. Okay. I think that's all I see. Did I miss anything? Okay, so let's do a little bit of math. Again, when I don't know where to start, I go to the thing I'm trying to find. I'm trying to find GM, and I look at its equation, and I look for a current in there, and I see I out. So I just kind of automatically, it might be the wrong decision, but I go for the current for KCL. And since CCS, 0 volts across it, no current there, no current there. So the first current I see is this GM VBE. And what's VBE?
VN.
VN. So this is just running out of colors. This is VN. Okay. So it's this current, but this current is defined as positive going down, whereas I want it going this direction. So it's the minus GM VN. So that's the current coming through this path. This C mu right here, it has a voltage across it, and it's Vn. Vn is moving, so we can't ignore C mu. So the current going through here, treating this as an impedance, that's supposed to be a Z. Treating this as an impedance, you know, the current going across here is Vn minus the voltage on the other side of the impedance. So Vn minus 0 over the impedance of this. Okay, and what you really want is I out over V in. So if you divide both sides by V in, you get that. And if I scroll down, can't keep the impedance in there, but you have your I out over V in, and that equals, this is a 0 here. So what you get is, if you factor out the V in, you get minus GM plus 1 over J omega C. So this actually becomes J omega C. And just like with the resistance that we found, big R out, just as a habit, it's good to pull out the old GM. So if you just had a common emitter, what's big GM of a common emitter?
Negative GM.
Negative GM. So I'm going to pull that out. So I get a 1 plus J omega C mu over GM. Okay. Is that a pole or a 0? Oops. Minus sign problem. Minus sign problem. Is that a pole or a 0?
0.
It's a 0. So that's where the 0 comes from. And the 0 happens when these two magnitudes are the same. So omega is 0. When does the magnitude, for what frequency does the magnitude of this second term become 1?
Zero.
Okay, when the whole thing becomes 0, but what about the second term?
Oh, when G, yeah, I don't know.
Okay, so
Do you
this,
just, oh, sorry. Do you just solve for S?
for omega, yeah. So to make this have a magnitude of 1, omega times C mu over GM, you want that to equal 1. It's the inverse of that C mu. So for, this is, you know, each time you could do small signal analysis to find the 0 of your common emitters or your gain stages, but it will, you can pretty much just memorize this equation, just like you memorize the resistance at a collector's RO, the resistance at a emitter's 1 over GM. You can memorize it like that. If you want to know where a 0 is, what you do is you look at transistor, you look at this capacitance, that's C mu, and you look at the GM of your transistor, you multiply the two, and that's where your 0 happens. Okay, so a couple more. I'm not going to get anywhere near what I was going to talk about, but that's okay. We have Friday. Okay. What happens when you have a 0? What happens to the phase?
Doesn't it go up to, sorry.
Yeah.
Does it go up to like positive 90 degrees?
Yeah, so it does the opposite thing of a pole. So when you have a 0, where you would have been going down with your phase, now it either goes up or it flattens if you have a pole and a 0. And that's something that will be important in a little bit. Will I get there? Will I get there? So let me try. I'm going to try to get there. I think we can do this. Those that have already heard of Barkhuizen's. So up to here, we've just been talking about poles and zeros in the circuit, and it had nothing to do with feedback. So up to here, it's nothing to do with feedback. Nothing to do with feedback. From here down, this is with feedback. Okay, and we're actually let's just talk about positive and negative feedback. Yeah, let's just talk about positive and negative feedback. Maybe we'll get here, probably not. Okay, so if you have some feedback, so negative feedback, I think we mentioned this before, but if I move V in up, let's say 1 volt, just as an example, then VI plus minus VI minus increases by 1 volt. Okay. And then if it's negative, then feedback moves VI minus up by less than 1 volt. So VI plus minus VI minus increases the final, this is not stated very well, increases by less than 1 volt. So what's happening here is the non-inverting input goes up by 1 volt. So that just increased the difference between VI plus and VI minus. But feedback, if feedback moves it up, and then the change in the difference between VI plus and VI minus is less than how much you moved V in, then it's negative feedback. So if you tried to change the difference between VI plus and VI minus by a volt, and the feedback came up and moved VI minus up, so the difference actually changed by less than a volt, that's negative feedback. Right? Positive feedback is, say you move in VA plus up by 1 volt, let's say your feedback moves it down, so the difference between VI plus and VI minus actually changed by more than 1 volt. That's positive feedback. Questions? Did we do this in class or just lab? Okay. So right now I'd probably have you turn to your neighbor and explain positive and negative feedback, but that's hard. Yeah, so if this changes by 1 volt and VI plus minus VI minus changes less than 1 volt, then negative feedback. Is that better? Okay. All right, so that's positive and negative feedback. All of the configurations that you've used so far have negative feedback. For them to work correctly, the inverting amplifier, the non-inverting amplifier, the voltage follower, all of them have negative feedback. If you had positive feedback, the amplifiers would actually fail. Right. So negative feedback for all those configurations, you know, negative feedback is a requirement. So let's look at say, I don't know what I'm doing here. Say you have 2 poles. What's your phase change for 2 poles?
Negative 180 degrees.
Negative 180. So what happens is if you have 2 poles, your phase shifts 180 and the signals that were negative feedback become positive feedback. They flip. So if you had this and you flip it, now it's this. You can see this, if this is negative feedback, this is going to be positive feedback. So at 2 poles, you can get in big trouble if you have your circuit hooked up with feedback. Because the signal just naturally, because of the 2 poles, flips, and now you have positive feedback and your amplifier will fail. Okay. So let me just state Barkhausen's, and then next time we'll finish that up. So remember, between each stage you have a pole. So if you have a diff pair and then a gain stage and then an output stage, there's 2 poles right there. One between the diff pair and the gain stage, and one between the gain stage and the output stage. So here's one pole, and here's another pole. So that's already 180 degrees phase shift. So what Barkhausen says, so whatever your lower frequency pole is, these poles won't be in the same place. What Barkhausen says, this is magnitude 20 log of gain. What Barkhausen says is, well, I know at 180 degrees phase shift, I'm getting positive feedback. But if the signal being fed back at 180 degrees phase shift, in other words, positive feedback, if that signal is so small that I can ignore it, then it doesn't matter that I'm getting positive feedback. So let's draw that in. 0 starts 94. So what happens is after that 180 degrees phase shift, if you draw a line up, and Barkhausen decided that it was 0 dB, that line, that at 180 degrees phase shift, if your gain is above 0 dB, then you're in trouble. now the signal getting fed back is actually bigger than your input. So you're in trouble. But if at 180 degrees phase shift, you're less than 0 dB, in other words, the signal getting fed back is much smaller than your input, then who cares? We can ignore it. So this right here, by Barkhausen's criteria, this circuit is okay. Because at 180 degrees phase shift, your gain is less than 0 dB. And I know that went really fast, but just one more question. Again, we'll go over this next time. But one question, how can a 0 mess this up?
A 0 would prevent like attenuation that's caused by a pole, so that it may end up being above the 0 dB line.
Yeah, a 0 will make this flatten out. It also brings the phase up, but depending on, that was a left-hand plane pole, right? No, it's right-hand plane pole. Anyways, I'll fix that next time. But yeah, poles can mess with you and actually make your circuit, you can use them to help your circuit or to make them worse. So I'll stop there, but that's Barkhausen's right there, and it only matters with feedback. You don't care, if there's no feedback, then who cares about Barkhausen's? Okay, kind of squished that in at the end there, but any questions?
Yeah, I have a question. So if you, like you just said, you put 0, wouldn't that not be an issue though? Because the phase changes as well, and it won't end up going to negative 180, right?
Okay.
So like there won't even be the issue of it being at negative 180 degrees in phase and the gain being below 0 dB. Like it wouldn't matter.
How honest should I be? I realized that I needed to check something, so I rushed it at the end. Can I clarify that next time?
Oh yeah, sure.
Okay, I'll make sure to have my story in line.
Thank you, Tina.
All right, I'll see you later. All right,
Yeah.
bye.
Thank
Have a good day.
All right, bye-bye.
Thanks, Professor.
All right, bye-bye. Thank you for the video reminder, the recording
problem.
reminder.